In this presentation, I'm going to be taking a stab at introducing and developing a new method of scientific investigation I'm going to call cross-conceptualization. And the purpose of this is to formulate very clear concepts in a science. Now, to say this crudely, but probably effectively, what I mean by proper concepts is because concepts kind of just generally sometimes means ideas, but here's, to start off putting this crudely, the way we use words in a science really matters. If you use words improperly, you'll be unable to capture key distinctions and similarities and facts within a given field, and then you won't make any progress. So we need a method of conceptualizing. Now, Ayn Rand already gives us standards for proper concept formation in Introduction to Objectivist Epistemology. And what I'm going to do is I'm going to take a lot of the standards which are implicit in that and form a particular applied method that I call cross-conceptualization. And this isn't necessarily something I'm committed to yet. You're sort of seeing me, you get to watch me try this method out and see if it works for a certain purpose, okay? If you've ever tried to convince someone of the objectivist concept of egoism, a lot of times you'll run into two really common arguments. Both of them are epistemological mistakes. One of them is when they say selfishness doesn't mean that. You don't get to redefine the word. This is, of course, when you try to explain, no, I'm not talking about selfishness in the way it's usually used, where you're screwing over other people in order to enrich yourself. I'm talking about when you respect other people's rights as a means of and work to benefit the self, because respecting other people's rights actually is in your interest. A lot of times people will say you just don't get to define the word that way. Other people will say this is just a difference in semantics. So both perspectives are, of course, wrong. Concepts aren't the given. Contra the first arguments, concepts aren't just given to us. They're man-made. You do get to choose your own concept. But just because you get to choose your own concepts doesn't just mean it's a free-for-all. We need to use concepts in a way that actually facilitates clear thinking and actually facilitates a proper grasp of the facts. And it's up to us to properly define concepts, to properly form them. Now, this is a problem in the sciences as well, not just philosophy. And what you get in the sciences is basically faith in existing conceptualizations. I once talked to an objectivist physicist, and I raised a question: why is angular momentum conceptualized the way that it is? Angular momentum is a certain concept of motion, of rotational motion, and if, like, say, a yo-yo is spinning like this, then the angular momentum is actually defined as a vector, an arrow that points along the direction of the along the direction of the axis along which the object is spinning down. So it's a vector, it's a quantity that has direction. And I just said, I'm not sure exactly why it's defined that way. Why is it conceptualized that way? And even an objectivist physicist said that's just the way it's defined, as though, this is just sort of irreducible. The conceptualization just is what it is, and somehow it works, and it's not that important why it works. There was just a misunderstanding or just a lack of understanding of the fact that at some point someone had to define angular momentum this way, and they defined it for a specific reason because it captured certain facts. And unless we understand why it was conceptualized that way, then we don't fully understand what facts angular momentum conceptualizes. By the way, I take a sloppy stab at understanding angular momentum in which one? Lecture 5 of the Inductive Summary of Physics. That was not... Angular momentum is very tough, and I still haven't fully figured it out, but there's some initial understanding of that in Lecture 5 of the Inductive Summary of Physics. So something in science that is really taken for granted is concepts. Especially in physics, is what, since I'm a physicist, I've actually noticed this. Physicists tend to take concepts for granted, just like the objectivist physicist in my story did. They reason from those concepts, and very rarely do they think about the proper way of forming a new concept or asking whether the existing concepts have been formed properly. But of course, as we know, forming a concept properly is a matter of life and death. If you form the concept of selfishness improperly, if you think that, benefiting, if you package deal together helping the self with hurting others, then the essence of morality is simply never going to be available to you. And most people today go around without understanding the essence of morality. That's a big deal. And it's the same way in the sciences. It just so happens that we're very successful in the sciences. So our conceptualizations are largely good, successful. But that doesn't mean we take them for granted any more than we should in ethics. If we're going to understand those conceptualizations, then we actually have to understand how those conceptualizations are formed and properly validated. So we're going to go through an exercise today which hopefully is going to shed light on that. This is kind of experimental. Yeah, and I'll talk about the rest later. So let me go over this. Concepts, of course, have to be based on observation, which from an inductive point of view means that we need the prior context of knowledge which made certain observations possible in order to understand a given concept. So what would be an example of this? Think of the example of the atom. The concept of the atom was only properly formed once we started understanding the particular mass ratios involved in chemical reactions. Okay? So you could say that to form the concept of an atom properly, you needed certain observations of the certain mass ratios. By the way, this is inductive lecture 7, the atomic theory of matter. Where I go over that. So you could say, oh, well, your concepts have to be formed based on observations. Here's the thing, that's not enough. Those observations, in order to be understood what those mass ratios even meant, you need to understand those mass ratios in the context of prior context of knowledge. And I've covered that. I've basically shown you step by step, or rather shown you through example, how to reason with, and only with, a prior context of knowledge. I basically kind of demonstrated that over the course of the Inductive Summary of Physics. But what I'm finding is that actually isn't enough either. Concepts have to satisfy a number of other requirements. To achieve this, I'm going to try out an exercise which I call cross-conceptualization. What do I mean by cross-conceptualization? Well, this term comes from the courtroom term cross-examination. You've probably heard that from dramas and stuff. Here's what cross-examination means in particular. Cross-examination refers to when one lawyer, let's say the prosecutor, starts to interrogate witnesses that are brought forth by the other side. So the prosecutor, during a cross-examination, will start interrogating witnesses that were brought forward by the defense. The idea of this practice is that the defense has already brought in a witness who presumably is going to give evidence that the accused didn't do it. But now we get to subject that witness to a different point of view, to the point of view that from the possibility, entertaining the notion that the defendant did actually commit the crime he was accused of. And so what we're doing here is, in the courtroom, we're looking at the same set of facts from a number of different perspectives. That's what we're doing in cross-conceptualization. We're going to put forward certain concepts that follow from observations in a science, but then what we're going to do is we're going to cross-examine them. We're going to come at each concept from the perspective of each other concept. And when we do this, we're going to make sure that each concept is consistent with all other concepts. We're also going to achieve a number of other things. We're going to make sure that any given concept, that our full set of concepts are able to capture all known existence. You're going to see how this works when I actually try it. We're going to make sure that our set of concepts is able to capture all the known similarities and differences between existence. So, for example, the classic example of this, of course, is that the common concept of selfishness doesn't allow you to capture the difference between Steve Jobs and Al Capone. They're both acting to enrich themselves, but you're not clear on the difference. You also want to be able to merge things that are actually similar. You want to be able to see that Howard Roark, Steve Jobs, and Isaac Newton, even though they're just three completely different people, you want to be able to see how they're similar. Why? So that you can see what selfishness looks like, what moral action looks like across a number of different examples. Like for me, I'm not so much of a Steve Jobs guy. I'm striving to be more of an Isaac Newton type guy. So what kind of selfish action is involved in being like Isaac Newton? Does it mean you're always chasing money? No. Does it mean you ignore money? No. There's all these things. And so if you're able to say, okay, all three of these men are exemplars of selfishness, of a life that was really purposeful and very purposeful towards a very integrated set of goals, then calling all three selfish has a certain utility. We want to capture similarities between known existence. You should also be able to have a set of concepts which captures all known facts. So all of these are just proposals. This is my way of trying to come up with a method which allows us to clarify concepts. What else? We also want to have clear definitions which integrate the reference and differentiate those reference from existence which are not reference. So, for example, Ayn Rand defined, morality as rational self-interest. Or I'm not sure, but that might be the way of doing it. So here's why you might define morality as rational self-interest. So first, you're defining the essence of it, which is self-interest, okay? But then you're differentiating it from classes, a set of things that people might have trouble with. So you're specifically saying, I'm not going to go on whimsy or hedonistic range of the moment fancy. I'm going to think out what's in my self-interest. So that differentiates objectivism from a number of other alternatives. We also want to define our terms or define our concepts, but specifically define them in terms of essentials. What that means is that we want to define our concepts in terms of their characteristics, but not in terms of just any old characteristics. We want to define them in terms of characteristics which are causally connected to the greatest number of other characteristics. So, for example, does morality involve honesty? Yes. Does it involve justice? Yes. Does it involve? It involves a lot of things, but you wouldn't want to bring all of these things up. You want to define in terms of the essentials. You want to say rational self-interest, the goal, self-interest, and the primary aspect of the means, rationality. Why do you want to do this? Well, because what that does is it identifies the maximum, it calls to mind a bunch of linkages between those characteristics and as many possible other characteristics of the class as possible, because all of those other characteristics are causally linked to the essential. So it's a way of thinking clearly. Okay. So this courtroom analogy, it's there to imply that every aspect of our conceptual framework has to be examined in the light of every other aspect of our conceptual framework. Okay? So I'm going to demonstrate this process on what I call first physics. First physics is physics on the perceptual level. So here's what I mean by that. It turns out that physics couldn't really move forward until some serious reconceptualization was possible. And physicists take all of these for granted. In fact, historically, Newton's laws were seen as a priori truths, which are truths that we just kind of know ahead of time without any observation, which is ridiculous because before Galileo and before Newton, people had Aristotelian notions of physics. And that's kind of what we're going to be focusing on today. Today we're going to be trying to derive physical concepts and physical laws from just the perceptual level. And we're going to ask, if we didn't know what we know today, then what would be the best way to conceptualize this? Now, the purpose of this is, number one, to demonstrate, to sort of crudely introduce the method of cross-conceptualization. I'm also going to be refining the method of cross-conceptualization. This is actually only the second time I've done this. This is only the second time I've tried doing this exercise. The first time was with a subject matter which was much more complicated than this, but it was pretty successful. It took a lot of hard work, but that was a new subject matter. So I didn't want to present the method of cross-conceptualization while trying to conceptualize a totally new subject matter. So instead, what I'm going to do it on physics. And I'm going to do it on first physics, the kind of physical laws that you might encounter when you really haven't thought about physics before. Where you've talked about balls flying through the air, you've talked about pushing on things, sliding across floors, movement. You've talked about all this stuff, but you have never tried to actually systematize it into a bunch of clear concepts. So we're going to see how that works if we try to apply some systematic method of conceptualization to first physics. Okay. So the way to think about this is, here's the way to motivate us. Okay. I'll fast forward to a certain point within the inductive summary of physics. At a certain point, Galileo is looking at the Copernican model of the solar system, and he basically says, yeah, this seems right, because when we look at the night sky, the planets aren't moving in a perfect circle in the night sky. They're doing this loop-de-loop thing. So it seems a lot like the sun is actually at the center, and our planet, and a bunch of other planets are moving around the sun. Okay. There's a huge problem with this, though, of course, which is that we seem to think that when you move, you feel the motion. Certainly different kinds of motion are felt. So what this is going to do is it's going to motivate Galileo to clarify his concepts in this field. So two of my purposes here is I'm going to show what kind of conceptualization work which was required to move from first physics, or what you might call Aristotelian physics, to Galilean physics, the physics that was required to actually move into Newtonian physics with an understanding of forces, how forces cause acceleration, how acceleration causes a change in speed, how changes in speed cause objects to change position, which then opened up the whole world of matter, of motion to us. So first what I'm going to do is I'm going to show you the steps of cross-conceptualization. I've done this before, like I said, and here are the steps. Okay, so step one, first conceptualization. So cross-conceptualization, it doesn't have very cut and dry steps at this point, and it might never have cut and dry steps. It's a dynamic process. It's kind of a loose set of, maybe even once I really refine this, it'll still be kind of like a loose set of rules which you can use to clarify your thinking in a given field. And let me tell you something. I encourage you to, even if this exercise doesn't end up with super cut and dry steps, I think you're going to get a sense of the method of cross-conceptualization, and I would encourage you to use this in your own scientific fields in order to get clear on the concepts of your field. I would encourage you, though, to only do this with some particular motivation. If you feel like you don't have good clarity in a particular field, that's when this is going to help. So here are the steps of cross-conceptualization. The first step is what I call first conceptualization. This is where you just list and define the concepts of the field. And you don't do it in any particular order, just in the order that comes to you. Now, the order it comes to you, a lot of times, the definitions of any given concept are going to trigger, oh, hey, I have to define that other concept. That's a good way to do it, okay? Now, what you're going to find is that your first conceptualization is going to feel unclear, sloppy. That's okay. Put it down. You got to put this stuff down. The only way to get clear on it is to put it down and then correct it later. Be willing to make mistakes. So here goes. I've never done this before. Well, I've done cross-conceptualization once, but you are looking at me doing a first conceptualization of Galilean physics, okay? So, or of first physics. So let's start with our terms. Okay, so in order to do this properly, I'm going to think about what sort of context we might be in. So I'm thinking of a Galilean context. I'm thinking of Galileo trying to get clear on motion. Why is he trying to get clear on motion? Well, he's trying to get clear on motion in order to get clear on why why we may not feel the motion of the Earth as it goes around the sun. And of course, the Earth, if it's true that the Earth is going around the sun, then the only way to account for the motion of the sun and stars over the course of a given day is to say that the Earth spins also. So why don't we feel the spinning? These are some challenging things that Galileo would have to think about. So maybe we can start with our notion of motion. What is motion? What is motion? How would Galileo think about motion? Would he be able to say that it was a change in position? Yeah. A change in an object's position. Well, of course, what is position? Okay, so Galileo then says, position is the location of an object. Okay, so this is a simple boo-boo, but it's a big boo-boo to watch out for while doing cross-conceptualization, is when you define a term in terms of a synonym. So position and location are the same thing. That's just another word for the same thing. When you find yourself kind of defining something tautologically by just repeating the same word or a synonym of that same word, then that's a sign you have to be careful. It means that either you've run into a primary, a concept that can be observed, a concept that can be observed, but it cannot be, but its identity is not reliant on the identity of some other thing you're aware of, then that's fine because it's just something you can see and you admit, well, there might be deeper causes of this phenomena, but I'm not aware of them, but I can see that this is a thing. So is position just an irreducible primary? Is position an irreducible primary? Galileo might ask that question. And now it turns out historically Aristotle had already worked this out, and I don't know how Aristotle did it, but I'm going to assume that that Galileo was able to reason to the same set of ideas. So when Galileo thinks about location, he's going to say, okay, well, location. Well, what does location mean? Can I reduce the concept of location? Can I explain the concept of location in terms of other concepts? Or does everything have to be explained in terms of this concept? That's going to be an issue of fundamentality, and we're going to talk about that as we move on, but this is the kind of thing to worry about. So position ultimately is not irreducible. Position is ultimately not reducible. Position is ultimately reducible, but I'm going to try something out. I'm going to say that Galileo tries to just explain this on its own, okay? So that Galileo is going to try to just say maybe this is irreducible. Maybe this is one of my concepts which is something that's visible, like it's perceptual, but you can't explain it in terms of some further known phenomena. So let's say he says that. Okay, so what else? Okay, so you could ask then, what is the cause of motion? So motion, position. Now, actually, the cause of motion doesn't come in until later. Until when we get to a step where we start asking about propositions, facts, statements which capture facts. Well, we've used the word object. What's an object? An object is a physical entity. So when we talk about this, we're not talking about a thought. We're talking about a physical entity which it has location, it can move, it can change location. So these are things which are perceivable. So we're allowed to simply refer to them without breaking them down to something else. So it's an ostensive definition. So physical entity, in some sense, physical entity, that's really all we have to say. So Galileo he's defined his terms. This isn't much, but we have identified that motion is a change in an object's position. Okay. Now, what are some other things involved? Okay, well, of course, there's force. force is the cause of motion. Now, if you know modern physics, you know that force is not the cause of motion, but this is something that had to be discovered. And I think in a certain sense, it is valid in an early context of knowledge to say that force is the cause of motion. Okay? So force. What is force? Force is when one object presses against another. Okay. So this, of course, tends to cause a change in motion, but that's going to go later. Okay, what about weight? Would weight be considered a force? The tendency of an object to press downward. Okay. Interesting. The tendency of an object to press downward. So remember, we're just conceptualizing basic facts which would be available to non-physicists or to a starting physicist. In some sense, every human being starts as a physicist so long as he's lived in the physical world long enough, which might exclude certain people who were raised during the coronavirus and just stayed inside for the majority of their lives. But other than those poor souls, most of us have experienced balls flying through the air and stuff like that. And so we have some, like, in order to become physicists, in some sense, all we have to do is just clearly conceptualize our existing physical concepts. And you can see I've already done that with 5, albeit crudely, of course. Any physicist is going to notice that this is not good enough. This is not good enough. Well, good enough for what? It's not good enough to produce the modern physical perspective. But as you see me struggling this, wielding only tools that I think Galileo had, you can see how hard this would have been. You can see the kind of process which would have been required to actually achieve even Galileo's perspective on these physical concepts. All right. What else can we do from here? What other concepts can we come up with? Let's see. Weight is the tendency of an object to press downward. Oh, okay. So this is interesting. We have weight. Weight consists of the object pressing downward. Force is when one object presses against another object. So weight is a kind of force. Okay, so in light of the concept of force, I've redefined weight. Weight is a force that some objects exert on objects beneath them. Now, I'm going to take this opportunity to tell you about one of my rules of cross-conceptualization. Whenever one concept is a subset of another, you put it as a heading. You put it as a subheading, okay? So I'll just add that for now. Alrighty, I gotta stop looking at myself. Very vain. All right. So are there any unanswered questions here? There are, but that's going to require our next stage, which is going to be propositions. So I'm going to actually move. So let me show you the other steps of cross-conceptualization. List and define the concepts of the field. So I did that, okay? But obviously Galileo is not feeling satisfied yet. But what else do we need to do? The reason Galileo is not feeling satisfied is it's not important that he isn't feeling satisfied. The important part is that he hasn't gained any insight into some of the questions he's asking. He's asking the question, would we feel the motion of the earth around the sun? Or not? And so he's realizing that, so one thing he could do is he could say, I need to just clarify all of my concepts of motion in order to understand what might happen in this case. Let's see if I can understand how motion works generally to see what happens in the situation of the Earth going around the sun. Would we feel that? And then spinning around in a circle. So let's look at some of these other things. So he's listed some concepts. What's next? Edit the definitions of the concepts and add more concepts based on things that come to mind that need to be conceptualized and distinctions which are discovered between the things when the concepts are defined. Okay, so for example, we realized that weight is a kind of force because we found that we were using this word pressing. Now, you know what's interesting is pressing simply means force. So that's a red flag. We're defining force in terms of, itself, basically. So what that means is that, this is one of those cases where you have an ostensive definition. You simply say, okay, this is force, okay? Force is when one object, so that's not a great definition. A state well, there we go. A state of contact between two objects tending to cause motion. So what you say here is you say it doesn't always cause motion, but it can. So, well, does it tend to cause motion? Is it a dice roll? Does it, no, like, which can cause motion. See, this is something that we can, like, when does it cause motion? Well, it tends to cause motion when there aren't, like, well, if, like, the object isn't nailed down, so, like, if I just push a box across the ground, then notice how I'm not reasoning with any kind of modern physics knowledge. I'm just trying to get clear on the concepts on its own. And you're seeing that, even talking about this basic stuff requires more clarity than, like, my first pass would generate. So you can see that this is the kind of process which may have led Galileo to clarifying these concepts and finding the answer. Okay, so and I'm not even past the first step yet. I'm still trying to get clear on these 5 lousy little concepts. So what else we got here? We got motion, position. I'm not satisfied with those definitions. Aristotle wouldn't have even been satisfied, but let's just say Galileo doesn't know how to get it for any further than that. Okay, object, a physical entity, fine. These are just things you can see, and I'm just going to say everything else is going to be stated in terms of these, observational concepts, and that's fine. You have to start somewhere, as they say. So, like, everything else is going to be explained in terms of, perhaps, these basic concepts. Now, what is a force? It's a state of contact. What is contact? So you can see, like, I actually need to define contact. So that's another thing. What's contact? A state where two physical entities are in adjacent positions to one another. Okay? So we've used the concept of position, so that's good. We've covered our base here. Position is, we've already said it, and we've kind of decided that, at least for now, that's going to be one of the basic perceptual concepts, which is going to define the rest of the field. Contact, it's when they're adjacent. Okay, well, what does adjacent mean? Well, adjacent is a certain kind of position, so we better talk about what adjacent means. Adjacent. Adjacent. What does that mean? It means next to. Um, Occupy. I'm just going to take a stab at this. This requires you to be uninhibited. You may try drinking during this first stage. No, just don't inhibit yourself. Don't try to get it perfect the first try. You're just not going to. No scientist did. He had to throw something out there, then correct. That's the whole idea of cross-conceptualization, is you throw something out there and you correct. Adjacent. Where they occupy a property of two objects where they occupy nearly the same position. Okay? So at this point, nearly the same position. That is not very helpful, right? So I'm going to say this. So why is that not helpful? Nearly the same position. You're saying that the position is nearly the same. You're referring to a particular characteristic, position, which is perceptually available, and you're just saying, hey, the positions of the two objects are like almost the same. They're as the same as you could possibly get without them like interpenetrating each other. So, well, like, do objects interpenetrate each other? Well, objects cannot occupy the same position. So you may add that as a corollary. So I'm gonna add that under my propositions actually. For positions, objects may not occupy the same position. Okay, because you might say otherwise they're just not an object. Objects cannot occupy the same position. So now that is false. Well, no, that's just something generally true that we've seen. It's just a characteristic of position, is that two objects don't have the same position. They don't, like in video games, they don't kind of like merge into one another. They don't like ghost into one another. So that's a thing. That's not something that happens. Does that ever actually happen? You could say that a man can walk through mist, but there's no evidence that the mist is occupying the insides of the man. You can pour water into a sponge, but we can see perceptually that the water is occupying the spaces between the body, the parts of the sponge's body. It's not actually occupying the same location. So this is the important kinds of stuff that you'd have to think about in order to begin first physics. Like, what do I even mean by position? What is position? What are some of the characteristics of position? Here's one of them. Object can't occupy the same position. And it's worth noting that these are observed facts. You're generalizing about position because it's true of every instance of position. You're not making some kind of claim that this is like an a priori truth. I know that like Descartes, for example, in the Meditations, I think he says something along the lines of like, he takes it as like a priori obvious that two bodies cannot occupy the same location. As you get deeper, the part of why I want to say this is that this has implications for modern physics. When you start to talk about the nucleus, when you start to talk about the nuclei of atoms, you start to wonder, okay, wait a second. Does the concept of like object which takes up space and excludes other objects at that position, does that even apply on this level? You might say no, because at a certain point of physics, we actually understand why two objects never interpenetrate. It's because the electron shells of the atoms in the surface of one object are repelling the electron shells of the atoms in the surface of another object. So what's going on here is not the atoms literally ramming into one another. Well, they are, but the ramming consists of an electrical repulsion, or it's the Pauli exclusion principle. I'm not sure which, or maybe both, but it's some kind of repulsive force on the atomic or subatomic level, which is the cause of this here principle I have highlighted, that objects may not occupy the same position. So once you start talking about electrons and nuclei and stuff like that, I think you have to start entertaining the notion that they do in fact, or they can in fact occupy the same position. And I would wonder if once I actually start understanding quantum field theory, if it is assumed that two quantum fields may be excited at one same position, which is the same as two physical objects being at the same location. So that's interesting to think about. Like you can see that fundamental principles which condition all of physics, which are still not fully understood today, like the causes are not completely unlocked. They're coming up even at the Galilean level of analysis, which is super cool. So what else we want here? Force, a state of contact, I was on adjacent, a property of two objects where they occupy nearly the same position. Ugh. So what you want to do is highlight stuff you don't. So what do I not like about this? I'm not 100% sure what I don't like about this. So anything you don't like, you just put in bold or somehow mark it and say, I need to come back to that. I don't like that. So it's a constant process of cross-checking. What else? Did I use anything nearly the same? Okay. If you have Rand's theory of concept formation, which I am working with, then you can simply say that by simple observation, man is able to notice measurements. He's able to notice differences in certain properties in the more and in the less of that property. So one property is distance. And so when we talk about nearly the same position, we mean the distance is very small. Well, that brings us to a new concept, which is distance. Distance is the difference of position between two objects. Okay? So this allows us to redefine adjacent. A distance of 0. We don't even have no distance from the parts of another object. I'm talking about the parts because let's ram my Apple Pencil and my yo-yo together for the 14th time. Parts of the pencil are touching parts of the yo-yo. Notice the inner surface of the yo-yo. So we're just trying to be precise. So it's, that's what adjacent means. Only parts of them have to actually be touching. Touching. Do we need touching? Touching is contact. What's contact again? It's a state where two physical entities are in adjacent positions to one another. What's adjacent? It's when they have no distance. Fine. What's distance? It's a difference in position. Okay, this is looking pretty sweet. So what's position? It's the location of an object. So then now at this point, you might start to say, well, wait a second. How am I even aware of location? Does an object have a position? Then, does an object have a position? Then another object has a position like a difference in position? Do they just occupy like different parts of the world, different like parts of space? Or is it that the location can only be specified with reference, the location of one object can only be specified in reference to another object? And so you start to think, okay, well, can't it just occupy different parts of space? Well, what's space? Let's think about what space is, baby. Space. The final frontier. No, space. What is space? I mean, would Galileo even have a concept of space? By the way, it's really hard to reason with someone else's context of knowledge, especially someone who is only just beginning to think about physics, someone who doesn't have the benefit of 200 years worth of people thinking nonstop about physics. It's hard to go into Galileo's shoes. So I could be making a lot of anachronistic steps of reasoning. This presentation is just not going to be perfect, but I think you're getting a sense of how cross-conceptualization begins to spider out and allow us to clarify each aspect of our grasp of a given field by integrating it with our grasp of each other aspect of that field. So let's continue. What is space? Space is volume, which is not occupied by objects. Okay, well, volume in this context is really just referring to space. Okay, well, can space be perceived? Well, is there like something I'm perceiving right here? There's air, but I'm not referring to the air. I'm saying take away my hands, take away the air that's here, and then the here-ness, that's what I'm talking about. Is that a valid concept? Can you even look at like the nothing that's there when can you even look at the nothing? Can you talk about the nothing that is there when you take away the something? So I think here's where we get to just borrow from Parmenides. Parmenides was a Greek philosopher who had a great statement. He said, that which is, and that which that is not. Nothing ain't a thing. So there's this stuff here. And I'm not talking about the air. I'm not talking about my hands. I'm talking about the stuff that's between my hands. Well, there's air between your hands, James. No, but I'm saying like if you take away the air. Well, if you take away the air, what's there? Well, nothing. Well, but nothing ain't a thing. So you talking about space? So, well, but then what the hell are you even talking about? So what we do here is we talk about this as dubious. Dubious, the word dubious derives from the Latin dubi, which is a marijuana cigarette. So when something is dubious, what we're trying to say is that it sounds like something, someone would come up with while smoking weed. So you mark any concepts that you feel that you have reason to think are dubious. Okay? Okay, how did we get into this mess? How did we get into this situation? You can see this just requires going over it and over it and over it again. The great physicists and philosophers of history did not get that way by sitting around and smoking a bunch of weed. That may have been, like what they did afterwards or something for fun, but it required a lot of work. So distance is the difference in position between objects. Okay, what is position? I'm saying that position is the location of an object. What's the location of an object, though? So when we're talking, it's the difference in position. Okay, but what is position? Now, here's a situation where you start to have a hierarchy. You start to have a question of hierarchy. I'm going to bring in another rule of cross-conceptualization that I told you about. As you define your concept, you will find that you are defining some of your concepts in terms of other concepts. Move such concepts higher on the list so that any given concept on the list is defined only in terms of other concepts of that field which are higher on the list. Here's the idea. What this does is that you're putting this in what I've in the past called a causal hierarchy, but now I actually call it a conditional hierarchy for reasons. The identity of distance is apparently dependent on the identity of position, apparently, in the way I'm talking about it. Now, part of the reason we want to do this is it tells us which ideas condition which other ideas. Which ideas are dependent for their which existents are dependent for their identity on other existents. What do I mean by dependent? That is not a good word to use. It's a kind of I'm kind of anthropomorphizing the inanimate matter out there. So what do I mean? To grasp the identity of distance, apparently, one must make reference to the identity of other kinds of existence. In order to grasp this, you are using position. Distance is a difference of position. That assumes that position is something that we can grasp like on its own. It's a primary that you just look at and you just say, that's one of them things, and I'm going to understand all the other things in reference to this thing. Okay, now you know what's interesting? It's almost like position is like one of the measurements of distance. Now, I don't think it is. By the way, I think this is going to end up being wrong, okay? Because position doesn't end up having any meaning aside from position with respect to another object, which means distance. But, maybe I should make this point later. But basically, here's the idea. I wonder if what you're doing is when you have to define one concept in terms of another concept, what's going on is you're using, in your definition, you're using other concepts to help you understand the concept at hand. What does that mean? What is a concept? A concept is a mental integration of two or more observed existents possessing a set of common characteristics, the characteristics differing only in degree. That's my way of sort of recapitulating Rand's understanding of concepts in my own terms. That might have flaws in it, but that's just what I'd prefer to use my own definition instead of just repeating Ayn Rand's, at least for now. The reason I'm doing that takes a while to explain, so I will stop there. Just know that might not be perfect since I gave it right off the cuff. So, but here's what I'm getting at with this. So Conceptualization is a policy. I think I heard that from Greg Salmieri. It's a good way of thinking about it. I'm going to treat these things as being the same in some regard. In what does it mean to treat things as the same? Well, they all have the same distinguishing characteristics. They all have the same characteristics which distinguish them from other things. Okay. So what I'm doing here is I'm identifying when I'm talking about a difference in position, I'm conceptualizing the distinguishing characteristics of this concept, which means, now what is a characteristic? A characteristic is an aspect of an existence identity. When you look at something, you grasp, perceptually, its characteristics. You are able to grasp the characteristics even if you have not conceptualized them yet. So, for example, when a toddler conceptualizes dog, and maybe dog is his first word, dog, duh. So he says dog, okay? He's noticing that there's these things that are unlike other things. They got these legs, they got the ears, they got the nose. Here's the thing, the kid doesn't know the words legs, ears, nose. But he sees legs, he sees ears, he sees nose, he sees these characteristics. He doesn't have names for them, but he can see them. He can see that Fido and Rover and Molly all have these characteristics. Molly being a dog's name sometimes. So, these all have the same set of characteristics, so he unites them based on those characteristics. Later, he may decide to clarify his concept of dog by mentioning some of the distinguishing characteristics in the definition. Of course, I don't think legs would be one of them, but you could maybe. So it depends on your purpose for defining the concept. But, that's all I'll say. My point here is, I'm not sure if I'm making it very well. My point here is that if you define one concept in terms of another concept, one reason you might be doing that is you're using another concept to describe the characteristics of the concept you're describing. So distance is a difference in position. What is position? Okay, well, position is, now what is position? Well, let's say that the universe was just this big old container. Well, let's not go there. Let's just, when I talk about an object's position, what do I mean? It's right here on the table. It's down the street. Well, what am I talking about? Well, okay, I know what I'm talking about. The distance of one object from another object. Okay, but now, and this is going to come up during your cross-conceptualizations, now we have a circle. Because we got distance is a difference in position, and then position is a kind of distance. So when you have circles like this, that's a sign that you need to reconceptualize. So what should we say here? Now, I'm having trouble thinking from Galileo's perspective, or from my fictional Galileo's perspective, because Galileo knew how Aristotle solved this problem. I'm going to just jump right to how Aristotle did this, which is to simply say, I'm going to get rid of... I'm going to actually switch these. I'm going to make distance the more fundamental concept, and I'm going to simply say distance is a relationship between two objects. And of course, I'm going to have to move object up here. I'm going to have to move position down. I'm going to have to move motion down here. Okay, so let's think about this. Oh, wait. We haven't. So let me explain this. Distance is a relationship between two objects. Okay, is it okay that I haven't defined what the hell that relationship even is? Yes, because as I keep saying, it's okay if your field has ostensive definitions. You're just saying, hey, you know what a distance is. Take a look. Like, that's fine. You have to end up referring at some point to just something that is the way that it is. Now, do distances have some kind of underlying physical cause? I think so. Everyone treats distance as irreducible. Now, from an epistemological perspective, I think it is. What do I mean by that? I mean, in terms of the way we grasp the world, when we talk about distance, we're just talking about this, okay? And like, we can't get underneath that yet. It's just a thing that is. It's a certain relationship between objects. I think there's more you can say about that, but this is fine. Just because we don't know of how to reduce that fact down, we can't find some kind of underlying physical cause of this thing, doesn't mean it doesn't have one. So I actually happen to think that distances have an underlying cause, which is really weird to think about. But it's not that weird to think about once you start asking the right questions. But one step at a time. Just because a phenomena has an explanation doesn't mean you have to give it. You can just use that as one of your basic things you define everything else with respect to. Okay. Motion is a change in the object's position. Position's coming later, so we need to move this. Space is a dubious concept. We're deleting it. We no longer need it because the facts, Rand's razor, by the way, I just used one of our rules. Be prepared to delete concepts which are redundant. That's Rand's razor. Cognitions are not to be multiplied beyond necessity. If we already are, when we talk about distance, if we're talking about this, and then position is simply the distance from of one object from another object, and then motion is just the change of position of one object with respect to another object. Like, do we even need the concept of space? Well, you can talk about like this cosmic, like, swimming pool we're all swimming in, but like, what the hell does that even mean? Is there evidence for that? Like, it's tempting to think of space as this container that everything is in, but there ain't no evidence of the container. There's just the things and the distance relationships between them. So you can see, I don't know if I'm demonstrating this with sort of like perfect inductive consistency, but you can see that you're getting a sense of how simply by comparing your concepts to one another, you can start to gain clarity about what the hell you mean. How do you achieve that clarity? Well, you rely only on observations, and you demand that your conceptual framework as a whole be able to, what did I say? Let's go back to the rules. Capture all the known existence, capture the similarities and differences between existence, capture all the known facts, have clear definitions which integrate and differentiate, which integrate things that are similar and differentiate things that aren't similar. I need to add some kind of rule involving, why one thing needs to be based on another thing. So I already have that written down here, but maybe I need to like be more specific about that. So as with a lot of the things I'm doing today, I'm not putting this forward as some kind of final idea, but this is a cool little thought. As you define your concepts, you will find that you're defining some of your concepts in terms of other concepts. Move such concepts higher on the list so that any given concept on the list is defined only in terms of other concepts of that field which are higher on the list. So, you're not introducing words whose meaning hasn't yet. As you're going from the top to the bottom, you don't want to end up reading a word whose meaning you don't yet know in terms of the rest of the system. Now, the reason you don't want that is when you define a concept in terms of another concept, you're using that higher concept you are using that, I don't like this, higher concept as the standard on which you measure. I don't know if measure is the right word, the existent at hand. What I mean that is like, let's go to the specific example. Position is understood in terms of distance. Why? Because I use distance to define it. I'm using distance as a standard, the standard on which I form or understand the concept of position. Now, eventually, to get clear on what that standard is, you either have to define it or point it out ostensibly. Or point it out ostensibly. Like say, it's this. That's what it means to be based on observation. It doesn't mean you need to have all of your words chasing other words in a giant circle of words. It means that your words refer to things, and one way to get your words to refer to things is to refer your words to other words, but then the words that refer to the words that refer to the words to refer have to at some point refer back to observation. Okay. Great. So we've gotten some real progress here. Adjacent, a property of two objects where the parts of some object have no distance from the parts of another. I think this is great. Motion is a change in an object's position. I think that's great. Position, distance of one object from another object. I think that's great. This is going to end up getting changed, by the way, but it's okay for now. Notice how you're kind of in a constant, at any given stage, it's almost like your concepts at any given stage are like, they're okay. Because they're good based on the stuff you've integrated so far. If you try to integrate more facts into the mix, that's going to require that maybe you have to change every damn definition you have. But for now, this is nice. We know what we're talking about now. Okay, contact. Okay, what's contact? A state where two physical entities are in adjacent positions to one another. Well, I mean, doesn't that just mean contact is adjacentness? Contact. Well, here's something interesting. Contact. Well, here's something interesting. Contact, the difference between contact and adjacentness is when we talk about contact, we're specifically talking about the force which occurs from the adjacentness, okay? So, So, we need to talk about contact forces. We need to come up with another species of force. How about them apples? Contact. A force where two objects press a state where two objects apply a force to one another. A state where two objects apply a force to one another as a result of being adjacent. As a result of being adjacent. Okay, well, this is interesting. That's going to lead us to a new proposition. Now, I'm already kind of bringing in Newton's third law, only a little bit. I'm saying that whenever two objects are in contact, they exert a force on each other. And I think it would, I jumped to that, but I think it would take you some thinking to end up there, but I don't know. I did it. I'm feeling good about my concepts. Let's go to some more rules. Okay, so we got more of our rules for our first conceptualization. We listed some concepts. We edited the definitions to make them consistent with one another. Here's something worth noting. When you are suspicious of a given definition but don't know how to change it, write your suspicion as a comment on that definition. So just write in the marginalia or use, Google Docs to write a comment. That's great. Be prepared to delete concepts which are redundant. Rand's razor, fantastic. We did that. Not too much, but we did it. As you define concepts, you will find that you are defining some of your concepts in terms of other concepts. Make sure you list your concepts hierarchically. I've gone over that a bunch of times. Order your concepts. The later concepts being conditioned by the earlier, and with subclasses always being put under the heading of the broader concept which subsumes them. Let me explain that. I've already done that here. We have force and we have two species of forces. Subsumption, that's when this is a relationship between concepts called subsumption. It's when one class is a subclass of a wider class. There are forces which are weight forces. There are forces which are contact forces. There's a little something I need to change here. See, this you're constantly just getting these little nuggets of clarification. You got to just, just feast on these little clarification nuggets. So, but what am I trying to say? So, as I said before, you're kind of like using subsumption is another case where you're using a higher concept as your standard for understanding the lower concept. Okay, so subsumption is just another species of that, and so you can label that as subcategories, basically. Okay, let's turn to what I think is kind of a problem. Weight is a force that some objects exert on objects beneath them. Contact is a state where two objects apply a force to one another as a result of being adjacent. Well, let's think about weight force. There's a weight force of this yo-yo on my hand. I can feel the yo-yo pressing into my hand. If I remove the yo-yo, I know that air is in contact with my hand. You might say, how does Galileo know about air? Here's how. He can feel it ramming into his face when he does this. Okay, so people know about air, even in Galileo's time. Okay, the air doesn't press on my hand. Now you might be saying, James, of course air presses on your hand. It has gravity. Galileo doesn't know any of that, all right? It's arbitrary for him to say that air has weight. No, air doesn't have weight. It's not pressing down. Okay, great. So is weight a kind of contact force? It's the pressing down. Now, you know, if you've done any physics whatsoever, then you know that weight is not a kind of contact force. But as it stands now, is there any reason to not call it a contact force? I don't see one. I'm going to have to subsume weight under contact force for now. Are there forces which are not contact forces? A state of contact between two objects which can cause... Oh, well, that's interesting. I defined forces as contact. So here's a circularity. And it's not a terribly interesting one. I just need to change this. Force, a state where an object acts on an adjacent object in a way which tends to cause motion in that object. So that allows me to just eliminate the concept of contact. Everything we need from contact is just inherent in adjacent and force. That's Rand's razored away. Force, a state where an object acts on an adjacent object in a way which tends to cause motion in that object. Okay, so this leads to some interesting things. This is going to lead to propositions pertaining to how force causes motion. I know that force causes motion. Now, as always, some of you may say, James, force causes a change in motion. Yeah, I know, but how did we figure that out? That's what I'm showing you, okay? So they had to reason through all of this. This is all totally valid within the context of knowledge. There's a ton of what you might call mistakes, but they're not really mistakes, because in order to get the full picture, you have to slog through a lot of these early formulations. You have to be willing to guess, check, and revise. Ayn Rand, when you look at Ayn Rand and you see how clear she was about everything, you might say oh, wow, I wish I was that clear, and it might scare you and make you think that you shouldn't try things. No, try it. Try things. Be willing to be wrong. Be willing to correct yourself over and over and over and over and over again. The more you'll know and the clearer you'll be, and you'll just be an epic badass like Ayn Rand was. So hopefully, or you'll get closer at least. So let's continue to get closer. Where was I? Force, a state where an object acts on an adjacent object in a way which tends to cause motion in that object. So what I'm doing here is I'm going to flag this. I'm going to bold it to say this is not really a proposition. When I get to my propositions, I'm just reminding myself, hey, we got to think about how force causes motion, and we're going to get to that real soon, baby. So, let's see. Let's do a little housekeeping here. Move that over. We are good. So we got weight as a particular kind of force. That's great. Are there forces other than contact forces? Well, are there forces other than contact forces? Let's think about that. Well, what about falling? I don't think they thought of falling as a kind of force, okay? At least it's not obvious to think of it as a kind of force. So, but you know what? It is something, so let's talk about falling. falling, a state of motion of some objects towards the center of the earth. Okay, and I think this is just fine. Aristotle had all kinds of erroneous accounts of what the cause of falling was. Like, he said that it was going to its natural place. He identified that as a kind of like purposeful motion, like it's like in its nature to strive towards the center or something like that, and that is a mistake. I'm going to remove that from... I'm just not going to make that mistake. Maybe I'm, making an inductive error by doing that. I'm missing whatever it is, Galileo had to get right in order to avoid Aristotle's error here. But I'm sorry. I'm just not going to be perfect in every way while trying to do my inductions. That's really what it comes down to. I'm just doing my best to do that. Future inducers can clarify these kinds of things, but for now I'm just sort of trying to identify what rules of induction I can, including here, cross-conceptualization. So, falling, a state of motion towards the center of the earth. Galileo was aware that the earth was a sphere, so he would have been like, well, Galileo being from Texas, of course, Galileo says, well, like, people in China are not upside down, so like down just means towards the center of the earth. Smarter people knew this, I think, and so the state of falling is towards the center of the earth. Oh, well, that's interesting. Down. That's interesting. See, down is just another physical concept, right? And it doesn't mean, it's not like an absolute direction. It's not like people on the other side of the Earth's sphere are upside down all the time. And they're like, wow, this is weird. No, like down is just towards the center of the earth for them. It feels the same for them as it does for us, because down just means towards the center of the earth, and down is just the direction things fall. We could even say, we could just define down as the direction toward the center of the earth. Well, now here's something. What is direction? You'll notice that, to define some concepts, you realize you end up having to bring in more concepts. And you're already tossing these concepts around. All of these, you're already using a lot of these concepts in, at best or at worst, a sloppy way, but a way that, isn't a complete disaster. You're still able to talk about physical situations, throw the ball down, smash his head down. You're able to say these things, if you're wrestling and command people how to properly wrestle, smash his head into the ground. You're able to smash. You have these words, they work in a certain context, but you're trying to clarify their meaning so that they can be used in the broadest possible context available to you. So that's another take on what the point of all of this is. Okay, what is direction? Direction. Well, we can start with an ostensive definition. Direction is the thing that's changing about where this thing is pointing. Direction. So for now, well, here's something interesting. When we say it points in a certain direction, direction is also relative. What is the direction of this thing? We can talk about north, but north simply refers to the direction that a compass points. I think they had compasses back then, but let's just say they did. The compass always points in a certain direction, and so when we talk about the other directions, those are always in reference to the other directions, so there's some distance that we're always making reference to. So direction is actually dependent on distance. Direction is a relationship between two distances. And it's this kind. Now, it would be great if we could define direction in terms of some deeper idea, but for now, that's all I got. And you know what's crazy about this is even in the modern day, I don't know if we have like a deeper way of describing this. We might, but we certainly have deeper ways of measuring it, like the Cartesian coordinate system. Or like that Cartesian coordinate system doesn't measure it, but it quantifies it. The Cartesian coordinate system, polar coordinate system, spherical coordinate system, they all quantify direction. It quantifies the difference between the distances, but it doesn't identify an underlying cause. So that's cool. What's the underlying cause of direction? By the way, I have a hypothesis, but I'm not going to tell you. So you'll have to keep watching for a very long time to get that. So let's see. So direction is just a relationship between two distances. That's all I'm going to say. Whew. So this is some pretty cool stuff, eh? Okay, so that's what down is. That's cool. Weight is a force that some objects exert on the objects beneath them. Beneath, I don't need to define the relationship between beneath and down. I mean, once you really want to polish this, you want to avoid slight differences like this. You end up wanting to use the same words over and over again, but I'm not going to be too much of a stickler on that for now, since a lot of this stuff, for all I know, this is all going to end up being rewritten. This is just, it just takes a long time to do this stuff. So, okay, so you can see at this stage that we got some pretty nice concepts. Let's start moving into some propositions. Let's look at first listing of principles. You'll notice there's a bunch of steps that I've put down for cross-conceptualization. We have now completed our first conceptualization. That does not mean we're done forming concepts. That means that we've gone through our first pass of concepts. We've done some stuff to make them consistent with one another. We've done some cross-conceptualizing. And now we're going to do our principles. Okay. Now, let me tell you some of the overview things for principles. The purpose of the cross-conceptualization exercise is not just to form concepts. It's also really this whole exercise, the conceptualizing part is only one aspect. The other aspect is the formation of propositions, which allow us to capture the facts of that field, okay? So really you can think of this whole process as a procedure for integrating our knowledge. In the inductive summary of physics, you've seen how each observation gives rise to ideas, which in turn gives rise to more observations, which gives us certain insights and raises new questions, new ways of identifying new facts. And then And then that leads to even more and more and more. Something I really do leave out in the inductive summary of physics is the integration phases. I think the integration phases kind of happen implicitly in between the steps, but a lot of work is required in between inductive steps to just clarify your concepts. And when you clarify your concepts, when you make each concept consistent with each other concept, when you make sure that you're able to conceptualize all of the facts which have been observed so far, you really make everything much clearer. And you end up learning new things. You learn a lot just by looking, and when you look, you start to conceptualize. You just start forming new words. You just say, oh, hey, like that's down. And, what direction did he walk? How hard was the force he pushed with? So, you just use these words. You just come up with these words because you're seeing things and you need to call the things something. But then, and that's the induction part. I mean, all of this is the induction part. But that's the induction part I've already showed you in the inductive summary of physics. But one thing I really didn't show you is how much thought is required between observations to clarify what it is you were looking at. Notice how Ayn Rand did not make any new observations, really. She didn't have a laboratory where she was making accessing aspects of reality which other people just couldn't see. She was seeing the same stuff everyone else was. She just conceptualized it much clearer. And what I'm doing is I'm giving you specific norms and ways of proceeding in your thinking process in order to get that same benefit Ayn Rand had. Another thing worth noting to connect this with objectivism more is that this is part of what is referred to as the spiral theory of knowledge. When you learn some stuff about forces and motion and position and all of these different things, you realize when you try to explain some of these concepts in terms of other concepts, you end up learning more. So, for example, we learned that position is nothing more than the distance from one object to another, and distance is just a particular relationship between objects, and that there's nothing more to it than that. The default, it seems, is to think that space is a container that all the entities of existence are dumped into. And so, that perspective can be thrown out the window, not through some particular observations, but through the spiraling integration which happens when you try to get all of your words to make sense in the context of the usage of all your other words. And that is cross-conceptualization. This is really a process which is kind of done naturally, but very few people do it because very few people in history have ever thought independently about concepts. They've only ever used the words other people have used in the way other people have used them. It is only the innovators who have ever come up with new words or rejiggered the way the existing words were used in order to capture new facts. But those few pioneers who engaged in that process were, in essence, engaging in cross-conceptualization. And that is why we have a really clear, useful set of concepts in many of the sciences, which allow us to, and that is just an enormous part, maybe 40% of what allows us to conquer nature. It's not sufficient, but it is necessary, and it's a huge part of the job. It's a huge part of the challenge, and it's a part of the challenge that I don't know if it's really ever been captured by anyone's work on induction. I mean, at least I haven't seen any of it. Oh, wait, no. McCaskey definitely talks about this. John McCaskey definitely emphasizes this in his papers. I'm giving you an explicit method for clarifying your concepts. So do this when you do science. If you're a scientist, or hell, even if you're a businessman, hell, you could be an accountant. Go through the concepts of your field. Do this exercise. See if you discover something new. There's probably just like a bunch of free knowledge just laying around for you to pick up once you actually get clear on this stuff. And tell me if you discover something new. It would be really cool to hear about. Like, I'm an accountant. I used your cross-conceptualization method, and then I realized that, numbers are like just an illusion, man. No, you won't come to that conclusion, but maybe you'll come to some actual deep conclusion. Okay, so let's see. Okay, let's conduct our investigation into principles. Start at the top of your list of concepts, and for each concept, write as many generalizations as you can think of pertaining to that concept. Okay, let's do it. Object, a physical entity. I don't know what generalizations I can say about this. Objects may not occupy the same position. I think that's fine. Objects have extension. Okay, now this is going to bring us to another rule of cross-conceptualization. As you write principles, you will find that you will need to add additional concepts to your list in order to capture the principles of your field. Add these concepts to your list and define them. Okay, so I just used the word extension. What is extension? Extension is really a kind of, let's see, positional relationship. Yeah. Okay, extension is the set of positional relationships between the constituent entities of a physical entity. So, when we look at this yo-yo, we can see it has that part, and that part, and that part, and that part. It's got all these different parts. If you consider the full set of position relationships between all of those entities, then it has extension. Objects may not occupy the same position as other objects. Objects have extension. I think that's enough. Saying that objects have extension is not a very helpful proposition to write down. We're going to Rand's razor that away because it's already just included in what extension means. So a lot of propositions just aren't required. You don't actually have to write them down because they just kind of jam up the works because they're already like so obviously in your definition or implicit in your definition that you don't need to write it down. You want to think eventually you essentialize this list so that you're not getting clogged up with a bunch of crap. And by the time you write this list over and over again and keep improving it, the list is just going to be seared so deeply into your brain meat that you don't even need to look at the list anymore. Probably maybe you need to reference it in order to just remember something, but that's about it. Okay, objects may not occupy. When two objects are adjacent, they produce a contact force on one another. Contact force, is that a particular thing? We're just going to call it a force because in our current conceptualization, all forces are contact forces. Propositions pertaining to how force causes motion. We definitely need to do that. We're going to get to that, but let's continue our journey through the various concepts in order to, write propositions about the different concepts. Okay, distance. It's a relationship between objects. Is there any thing we want to talk about with distance? I don't know. Direction between distances. Fine. Position. Any propositions having to do with position? I don't know. Extension. Any proposition. None are coming to mind. Sometimes this will happen. Sometimes you need to take a break. You're not supposed to do this in one sitting, but I'm going to do it anyway. No, I mean, this exercise will probably end before I'm done with the exercise. Motion. It's a change in an object's position. Okay, well, a change in an object's position. Do we have anything to say about motion? Well, we can ask, what is the cause of motion? Now, I've already talked about this, but what I'm going to do now, I already know I'm going to ask after the cause of motion. Let us ask after the cause of these other things and see if anything comes to mind. Okay, extension. Are we aware of what the cause of extension is? Well, that seems that's just a property of the object. The object has an extension because of the way it was shaped, but I can't think of any interesting physical generalizations that might pertain to the cause of extension, so I'm going to move on. What's the cause of position? Well, that also doesn't exactly make sense. It makes sense, but we already know we're going to be talking about motion soon, so yeah. When I ask after causes, it can mean two things. If you're doing induction, then it means maybe you go out into the world and start making more observations in order to identify the cause. But during the integration part of induction, which is what we're doing right now, this cross-conceptualization is part of the integration phase of induction. During the integration phase of induction, what you will find is that you might be able to explain some of your propositions in terms of other propositions. You might be able to find the cause of them. And you might be able to do that without making any additional observations. That's kind of like low-hanging deductive fruit, which is really nice to find because it's it's relatively easy knowledge to pick up. Distance. Is there a cause of distance? Is there a cause of object? Okay, so we're fine. Okay. What's the cause of motion? Let's get right to it. Propositions pertaining to how force causes motion. Okay. Let's think about this. So, right off the bat, we're going to write a proposition that's going to make anyone who knows anything about physics turn a little red, which is to make the generalization force causes motion. Now, I will maintain that this is... Well, I'm going to say, at least for now, and during this phase of our integration, this is a valid proposition, okay? Now, force causes motion. Now, it certainly sometimes causes motion, but does it always cause motion? No. So let's say force sometimes. Okay. Now, this leads to a natural question. So, okay, that's not a proposition, that's a question. So, I'm going to copy this, delete it as a proposition, and then I'm going to add it as a comment. So, unfortunately, I'm going to have to zoom out and subject you to tiny font. But I really like the comment feature on Google Docs because of obvious reasons. I'll just say this. It's really good for cross-conceptualization, because what you can do is you can, like, with cross-conceptualization, you end up being like overwhelmed with about a million things that seem wrong all at once, and you really have to just triage it. So what you do is you just flag things. So, okay, I'm going to ask this question. I don't feel like I'm ready to answer it. A lot of times you don't feel ready just because you're feeling like overwhelmed with just the sheer volume of questions you feel like you have to answer. So you just like kind of write them all down. You try to answer them one at a time. Sometimes the answers to some of the questions end up helping you answer the other questions, and you can just kind of whittle it down from there. I should let you know that I've only done this exercise of cross-conceptualization once before, and never to completion. So it remains to be seen if this is the exact utility of this exercise is yet to be seen. I have no doubt it's good for something, though. So that's what I'll say for now. Force sometimes causes motion. Well, when does it cause motion? Well, I already have a way Galileo might say this right off the bat. Okay, when a physical object is subject to a force, it will move if unimpeded. I think this is a good initial generalization. So it'll move if unimpeded. It'll move if other objects aren't in the way. Okay, so here's the deal. We just used the word unimpeded. So what's impeded? Impeded is when one thing is in the way of another thing. Okay, well, and that gets us to the whole idea that two objects can't occupy the same location. So like, what is impediment? Well, like, this thing's moving. Oh, but like there was another object in the way. So like, but that's just another force. So when a physical object is subject to a force, it will move if there are no other forces, maybe. Okay, but well, here's the thing. What about two dudes both pulling on a rope in the classic game of tug of war? In such a game, one man will prevail. Why? Well, he was stronger. What does stronger mean? Stronger meant he could exert a greater force. So when a physical object is subject to a force, it will move unless it is also subject to a greater force in the opposite direction. Okay. So, well, here's the thing. If it was subject to a greater force in the opposite direction, wouldn't it move in the opposite direction? So let's say equal. An equal force so look at this. When a physical object is subject to a force, it will move unless it is also subject to an equal force in the opposite direction. Okay. It will move unless it is also subject to an equal force in the opposite direction. Okay, well, what does equal mean? Equal means, now this isn't a physical concept. It means to the same extent. What are equal forces? Well, let's write that down as a concept. Equal forces. Forces which have the same power to cause motion. Okay, so these are some crappy concepts by today's standards. Even by Newton's standards, these are pretty crappy concepts. But it's only by cross-conceptualizing and going through a lot of iterations that it's possible to reach a conceptualization which is actually able to capture everything. So by the way, let me point out some things. So like we've done a lot of work, okay? We've done a lot of work and we've made a lot of progress already. But it's still a far cry from it's a far cry from even what would have satisfied Newton. Certainly would not satisfy a modern physicist. Why? What are we missing right now? Well, look at this. When a physical object is subject to a force, it will move unless it is also subject to an equal force in the opposite direction. That's wrong. It's right. Well, it's right in a certain context. It's right in a certain context, but Galileo knew that this was wrong. He knew that a force causes a change in motion. Force is not required for the maintenance of motion itself. But how do you think he got there? I think he had to go through a process of thought like this. He probably didn't sit down one day and just do it like I'm trying to do right now. If he did, he would have gone slower than I am. But I think he probably would have gone faster than the actual historical Galileo did. Galileo did this process. I'm guessing Galileo didn't have some kind of systematic process of cross-conceptualization. Maybe he did, and he just didn't. Maybe I just don't know about it. But I find it more likely that he was just kind of thinking about this over the years and investigating really intensely in other ways, asking certain questions, finding that he needed to reconceptualize in order to make things clear. And then he eventually ended up formulating some of these really key laws like, objects in motion tend to stay in motion. That's what I call Galileo's law of motion, which today is called Newton's first law. But I think if we want to credit the discoverer, we should call it Galileo's law of motion, because it was huge. It just opened the door to so much physics to realize that motion didn't require a force for its maintenance. And I think we're about to get there, by the way. And maybe I'll end the exercise once we reach that truth. Let's continue with our principles. So when a physical object is subject to a force, it will move unless it is also subject to an equal force in the opposite direction. Is there ever a exception to this? Well, whenever an object moves, is it being pushed? Whenever an object is subject to a force, but not an equal and opposite force. Well, let's just write some other principles which just follow from this. When an object is subject to a force, it will move in the direction of the force. What does it mean for a force to have direction? That's an interesting question, but I'm just not going to go through it for now. When a physical object is subject to a force, I don't know why I'm calling it a physical object. When an object is subject to a force, it will move unless it is also subject to an equal force. It will move in the direction of the force. Okay. Fine. I'm essentially skipping to the end since I'm tired. So at this point, maybe Galileo asks the question. So you can write your questions here. So actually, I should add that to one of our principles. So two things I'm going to add to the method of cross-conceptualization during our first listing of principles. Ask about the factors which condition each of the concepts in your list and any propositions you have written down so far. See if you can explain these concepts or propositions in terms of existing concepts and propositions. And of course, write down, like, if you find that you need to bring in new concepts in order to explain a given concept, go ahead and do it. I mean, in a sense, you already have those concepts, but you're just explicating them. You're putting them down onto your cross-conceptualization so that they can be explicitly integrated with everything else. Ask any open questions you have in your field. Fine. Okay, question. If the Earth were moving around the sun, would we feel it? Feel the motion? Well, here's another way to ask it. Why would we feel the motion? Okay, here's why. Because force is required for motion, the Earth would have to push us along to keep us moving with the rest of the Earth. We would feel a force like that. Since we in fact feel no such force, we know we aren't moving around the sun. Okay? So, there's the argument. There's the argument against the heliocentric hypothesis in terms of a decent conceptual framework. Not a good one, a decent one. Now, Galileo would then have to ask, is this actually true? Force is required for motion. Okay, well, let's see. Let's take a look at something. When an object is subject to a single force, it will move in the direction of the force. Okay, yeah, that's true. Remember, Galileo doesn't have a separate concept for motion and acceleration yet, BT dubs. He would if he started dropping objects and figuring out how they were speeding up, but let's just say he doesn't have that now. He just doesn't have a difference between motion and a change in motion, okay? So this is fine. It's not fine if we want to get to Newton's level, but it's fine for capturing the facts we're aware of so far. When an object is subject to a single force, it will move in the direction of the force. Okay, now, this is not the same statement as this, says Galileo. Okay, fine, but is it true? Is force required for motion? Okay, well, here's a question. Are there objects which move even though they are subject to no forces? Arrows. He's going to realize that, when objects fall, they're subject to a force, their force of weight, but we're not going to bring that in just to keep things simple for now. Arrows. Objects sliding to a stop. Their motion having not terminated. What else? What are some other objects which move despite having no forces on them? Well, but arrows might have a force on them. Descartes thought that there was a whoosh of air behind arrows. There's no evidence of that, though. So what you might say is arrow, perhaps the air pushes arrows along. Do I know this is true? No. Okay, so, and then what you can do is you can just do an experiment where you shoot an arrow past someone's hand. It's kind of dangerous, but if you do it right, then you don't have to worry. And just try to see if you can feel the whoosh, to see if there's air. I mean, the other thing that's the problem with the whoosh is like, why would the twanging of a string and shooting an arrow, like, why would that cause like a moving whoosh of air? So I don't know. I feel like I could have a whole debate about that from the Cartesian / Galilean context of knowledge. But I'm not going to, because it'll just, I think I can get to the right answer quicker. So, but let's think about objects sliding to a stop. An object sliding to a stop. Let's think about such an object. Let's think about an object sliding to a stop. An object which is sliding to a stop. An object sliding to a stop has no forces behind it. None that we know of anyway. There's no evidence of any such force. I've given it a force, and now the force is in fact this way, okay? The force is this way. Now, I think a little bit more cross-conceptualization than I've already done would really be required to identify friction as a force, this rubbing as a force, but like, why is it slowing down? You can ask, well, what's the cause of it slowing down? Well, objects that aren't getting pushed on tend to slow down. Okay, well, let's write that down as a law. That's how it works. That's a law. Let's put it down. Okay? Objects with no forces acting on them will slow and come to a stop. Okay, so that's contextually true. That's contextually true. But you can ask why. Why do they slow and come to a stop? It's scraping against the table. It's scraping against the table. Okay, well, the scraping is a force. Now, we may need to add scraping to our concepts, but I'm going to just focus on reaching the primary Galilean conclusion here. So, when an object slides across a table and comes to a stop, there actually isn't no forces on it. There is a force on it. Well, that's interesting. Are there any cases where an object comes to a stop? So you can ask this question. Well, you can think of a boat moving through the water and eventually coming to a stop, but we know that water provides some amount of resistance as an object moves through it. What are some other things that we can say? What are some other examples that we might dig up for like when an object comes to a stop when there's no forces on it? Can I even think of any cases where an object has no forces on it? Yes, an object simply at rest. Think of just a yo-yo sitting there on a table. in such a case, there are no forces on the object. There's a force upward. Well, and that's kind of interesting. Why doesn't the force... Well, maybe we won't talk about that. The object simply doesn't move when there's no forces. So like when there's no forces on an object, it won't move. So maybe we can add that. So we're going to delete this because like when objects are slowing down, well, here's something interesting. Forces can cause objects to slow down. Okay. Well, forces can cause objects to speed up. Okay. So that is interesting. Objects with no forces on them will not move. Objects with no forces on them will not move. Okay, what else could we... So let's go through this. I'm intentionally going a little bit faster than I should right now in order to get to a nice natural stopping place. Just know that that's kind of an artificial element of this presentation I'm giving you right now. Don't do this while actually cross-conceptualizing, because that's a good way to get biased, to try and like reason your way to a conclusion you were trying to kind of preordain beforehand. But I'm going to do that just to show you what it looks like to get to the end, to get to a nice new conclusion that cross-conceptualization might reach for us. And I think you can see that cross-conceptualization really could allow Galileo to get here. Okay, great. So when an object is subject to a force, it will move unless it is also subject to an equal force in the opposite direction. I mean, that sounds fine. When an object is subject to a single force, it will move in the direction of the force. Yeah, that's true. But is that separate from this fact? Forces can cause an object to speed up. Well, I can actually merge these two statements. When a single force acts upon an object, that object will speed up in the direction of the force. Is that always true? And Galileo would be able to see that, yes, that is always true. Only the thing is like in everyday experience, we actually don't see instances of no forces. We always, like at best what we see is pushing some object and then the force of grinding against the surface. We don't have the word friction yet. The force of grinding against a surface opposes that force. So what can he say? He can say, so we don't know what happens when a single force acts on an object. When two forces act on an object, that object will speed up in the direction of the greater force. That object will speed up in the direction of the greater force. When a moving object is subject to a force, here's the thing, on what basis, here's just a problem with this. This is something Galileo would just have to answer. On what basis is he calling the grinding force of like an object grinding against a surface, friction? On what basis is he calling that? Is he classing that with the same as pushing and falling? I'm sure there's an answer to that, but I haven't explained it. When a moving object is subject to a force opposite opposite the direction of its motion, it will slow down. Then when it comes to I'll just say that. Okay. Objects with no forces on them will not move. Is that true? Well, again, I'm not even going to write that because I ain't never seen objects with no forces on them. Okay. Well, and then we could do a sub-principle. The greater the force, the less it will slow down. If the object has no force, if the object has no forces on it, what will it do? I mean, that's not the right way to motivate this question. Here's what Galileo could say. Here's what Galileo can say. He'd say, okay, if the Earth were moving and men on its surface were also moving, what force would cause the men to naturally slow down? Well, normally, the thing that causes an object to naturally slow down is as if it's grinding against a surface. But the men on the surface of the Earth will not grind against the surface if they are traveling along with the Earth. So, there would be no such force. Wouldn't the men and the Earth continue forward despite the lack of forces upon them? So a man standing on the Earth, we know one thing for sure, he's not experiencing any forces. There's the gravity thing, but we're not going to worry about that right now. That's not the direction of the force we're worried about anyway. So he's just moving. Well, we don't know if he's moving yet, but we know he's not experiencing any forces. But if the Earth were moving along with him, would he need to be pushed? Would he need to be pushed along in order to move? Well, and then we can examine some kind of situation that's like this. What about a ship? Does a man on a ship require the ship to move, to push him No, he does not. But, let's say he gets when the ship speeds up, the ship does push on him. He lurches. The ship does push on him. And I'm coming to this way too quick, but you can kind of see schematically how I'm getting here. So what he can do from here, what is he going to do? He's going to add this last force. He's going to add this principle. An object in motion stays in motion. A force will cause an object to change its motion in the direction of that force. Okay, so we have a couple principles. We have these major Galilean principles that are just totally critical to later science. Okay, let's go through our propositions and delete the bad ones. Objects may not occupy. Fine. When two objects are adjacent, they produce a force. Fine. When an object is subject to a force, it will move unless it is subject to an equal force in an opposite direction. Okay, well, we need to add like an equivalent to this law. When two forces act on an object in opposite directions, the object will change its motion in the direction of the greater force. I'm arriving at that way too quickly, but you can kind of just imagine me doing this for another 9 hours and maybe the same kind of thing for another 9 hours, clarifying my concepts and getting to this point. When an object is subject to a single force, no, we already covered that, but in better detail using change in motion. When an object is subject to two unequal forces, it will move in the direction of the greater force, but with less. We already covered this, but we need to, like Galileo's going to say, we need to talk about this in terms of speeding up and slowing down. When a moving object is subject to a force opposite the direction of its motion, it will slow down. I think I already covered this in a different one. A force will cause an object to change its motion. So, we can... the greater the force, the less it will slow down, the more it will slow down. So this we would need to we would put it down here. It would end up getting subsumed into the other other propositions with respect to Rand's razor. Let's go ahead and do that. I'm getting tired and I want to cut corners, but let's finish this good. When two forces act on an object a force will cause an object to change its motion in the direction of that force. If we understand this properly, then this is obsolete, but we need to add a sub-principle. The greater the force, the greater the change in motion. So notice how this is only applying to an object with one force on it. Okay. When an object is moving, okay, so this one was Rand's razor. Rand's razor cut that one away. When two forces act on an object in opposite direction, the object will change its motion in the direction of the greater force. Yeah, great. The lesser force will reduce the change in motion, which would have been caused by the greater force had it been acting alone. Okay, I don't like this. So this is, on one hand, this is good because it captures a certain kind of fact. But on the other hand, we know that formulations which are better and more in terms of essentials are going to end up superseding this one. But you know what? I'm tired, so that's going to have to be good enough for now. I'm going to add one more principle to the cross-conceptualization, which is, what is this? Oh, yeah. Let's add Rand's razor as a method to the method of cross-conceptualization. And that tells us to integrate principles together into single principles when possible and delete redundant principles. That's just Rand's razor with regard to principles. Whew. So that's a good thing to do. I have not ordered the principles in terms of conditioning relationships, but that would be a good thing to do. Maybe I'll do that in a later cross-conceptualization exercise. But this is good for now. I'm going to publish the final product here. What was the final product? The final product is this list of crappy concepts and crappy physical propositions. I'm going to publish that. Now, they're crappy by today's standards, but they are absolute gold by the standards of someone trying to understand these issues by just looking at things. You can see that you could have achieved the same thing Galileo did if you used cross-conceptualization and a lot of time and effort. I'm also going to show you some of these rules. So what we've seen here, this is the method of cross-conceptualization. You can see that despite the fact that this is only the second time I've done this, and despite the fact that I completely did this with no prior preparation, I prepared a little statement on what cross-conceptualization is, but this is like literally the first time I've ever tried to cross-conceptualize basic physics. You can see despite all of that we've moved from a context of knowledge which involves only the things that are just immediately perceivable to people, all the way to a Galilean context of knowledge, where we are now aware of the fact that force is not required for the maintenance of motion, but rather force causes a change in motion. Now, you could certainly argue that because I knew the answer ahead of time, I was biased, and this worked out way better than it should have. I want you to be the judge of that. I mean, I'm going to be the judge of that once I edit this down. But you can see that, I think you can see that even if I didn't have this huge advantage, I would get somewhere using this method. This would help me somehow. It allows me to spiral around and get consistent on the way I'm using my words. And if I'm consistent about the way I use my words, I can start capturing more of reality in a more consistent way, and then start to notice some of the things I think that actually on the margins contradict other things that I know. And I say, wait a second. There's no evidence that there's some whoosh that follows the arrow around that keeps it moving. Like, Descartes, where the hell did you come up with that stuff? So, this and through thinking in this way, you can discover new things without ever making an additional observation. That being said, you have to have just like a giant stockpile of observations that you are ready to reason with. So, that's what I'm going to say for cross-conceptualization. I encourage you to use this method in your own field and let me know. Hell, make a video like this one. Use OBS, Open Broadcasting Software, and draw a boring list like this, talk in front of the camera for 3 hours, and see what happens. Send it to me. See if you can clarify the concepts in your own field. So with that, I'll end today's exercise. I hope you gained something from this. And I think cross-conceptualization has some real potential as a step in a method of induction. And for that, you can stay tuned for my induction paper, which hopefully will be which will be made public. The first edition will be made public on May 1st of 2022. Is this year 2022? I don't know. Maybe. I forget. I'm going to have a drink. Good night.